Today we will be going to module 2 of Physics 121. I want to quickly ask a question. What comes to your mind when we talk about electricity? Of course, you might be thinking of the challenges that is being faced by most African nations. You might be thinking of the challenges that you are currently facing as a result of taking lecture online. However, the basic theory and principle guiding this electricity might be alien to some of you. Hence, in today's course, I want to crave your indulgence to pay rapt attention as I take you through the basic introduction of electricity. What is electricity and what can you learn or you need to know on electricity? So very quickly, the intended learning outcome for today's lecture will be that at the end of this lecture, you should be able to describe electric current in metals. Metals are basically conductors. You should be able to explain Ohm's law. You should be able to explain factors affecting resistance of a wire. You should be able to understand the relationship between resistance and conductance. Resistance and conductance. Also, you should be able to understand the relationship that exists between resistivity and conductivity. You should be able to understand what is known as superconductivity. And lastly, you should be able to calculate equivalent resistance of series and parallel resistors. We might not be able to touch the last part of the internal learning outcome today. By next week, we will be able to complete that. Okay, so let's look at electric current in metals. When we talk about metals, what comes to your mind? You talk about conductors. You talk about materials that allow the flow of electrons through them. Or if you want to put it the other way, you talk about materials that allow electricity to pass through them. When you talk about metals or conductor, you are also talking about materials that are good conductors of heat. And so, the in question here are metals. They are different from non-metals, which could either be insulators or semiconductors. So metals is our interest this morning, or this afternoon rather. We are interested in looking at electric current in metals. And electric current is defined as the rate of flow of electric charge in a region or in a portion of a metal or conductor. The rate at which electric charge flows is what is referred to as electric current. Now, the flow of charge is possible in conductors because conductors contain free electrons. Flow of charge is possible in conductors because it contains free electrons. Unlike what you have in non-metals, especially insulators, there is no free electron in the constituent material of insulator, hence they cannot allow the flow of charge through them. So electric current is measured in ampere, and ampere is named after a French physicist and mathematician by the name André-Marie Ampère. André-Marie Ampère. So the unit of measuring electric current is ampere, which is abbreviated as A or AMP in some cases. And 1 ampere of electricity is equal to a flow of 1 coulomb per second. I repeat, 1 ampere of electricity is equal to a flow of 1 coulomb per second. And the quantity of charge is given as the current multiplied by the time it takes to flow. So if I take this equation, for instance, and I make I the subject of my formula, then I will have Q divided by what? Divided by T. And so the flow of 1 coulomb, the quantity of charge per time seconds, is what gives us 1 ampere of electricity. A steady current is one that has constant magnitude and direction. When you say a current is steady, it means the magnitude is constant and the direction of flow is also constant. So mathematically, we can rewrite the equation that I gave you earlier as change in quantity of charge divided by the change in time as electric currents, as you can see in this equation. So electric current I can simply be defined as the rate of change of quantity of charge that is stored or that flows in that material. The reason for the presence of conduction electron in a metal is because the outermost shell of metals have electrons that are not tightly bound. For instance, when you are writing in your chemistry, when you are writing metals, you have something like Al3+, meaning aluminium has 3 electrons in its outermost shell instead of 8 that is required in the outermost shell to make it a balanced atom. And so with that, you have 3 electrons who are willing to go, who are willing to move around. And so that is the reason why conduction takes place in metal. And as such, when a PD, a potential, is applied across a metal, those electrons are free and they can easily drift towards the positive terminal, hence giving a flow of charge through the metal. However, insulator have their electrons often and usually filled up, and so they don't have free electrons in the outermost shell that can easily cause electric current to flow in them. Let's consider a situation where you have field that is acting towards the left and the motion of the free electron is acting towards the right. So we can say that the electron will move with the same constant velocity v, and it will move in time dt. Okay. Hello? Hello, can I have your response?
Sir, we can hear you.
Okay, somebody sent a message. You can't hear me, you can't see my screen. That should be a problem from his end, I believe so. So can I go ahead? We are together, right?
Yes, sir.
Good.
Yes, sir.
Good. So let's quickly go on. Now, so you have constant velocity v and a change in time dt. And if we compute the distance from these two variables, well, we have our distance to be velocity multiplied by time. Do you agree with me? Velocity is the rate of change of what? Of displacement. This time around we're looking at the distance. And so your distance will be equal to velocity multiplied by the change in time. Is that okay? So in this same time, the number of electrons crossing any plane in the material in question can also be calculated as a v dt. We have v dt up here. I believe you are following me. And coming here, we have it multiplied by what? A. Where A is the area multiplied by what? The distance. The formula for volume is what? Is you have area multiplied by distance. Is that okay, everybody? Is that okay, everybody?
Sorry, cast.
Is that okay, everybody?
Your screen, sir.
You can see your screen, sir.
Are you seeing my screen?
But we can't see your screen.
You can't see my screen.
No, sir.
Yes, we
Sir, we can't see the
No,
screen.
we're not seeing it.
Okay, let me go over again
Sir, we
and
can't see
share
the
my
screen.
screen.
See it, sir.
Just a minute. Hello. Now, somebody by the name Saint Aduko has taken over presentation. He wants to lecture us. Maybe that person should continue. Why do you play with facilities available to you? Okay, this is not the time to discuss that anyway. It's one of your colleagues that is causing this problem.
keep quiet now.
Can I continue now? Do you have my screen?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
And please, I want every one of you to be guided.
Yes, sir.
Don't fiddle with the tools available to you. Otherwise, you are distracting this lecture. This is not the time for you to try out some of the tools. At your own leisure time, you can try it out. But not when the lecture is going on. Is that okay? And like I said, this session is being recorded. Every activity is being captured. So, you know what that means. You know what that means. Okay? So, we quickly move ahead. So, from here, we can calculate the volume. Right? So in this same time, the number of electrons crossing any plane in the number contained in this section of the length of the wire. The length of the wire is this distance we have calculated here, which is VDT, right? If you multiply it by the area, then we will get the volume. Okay? If there are n free electrons per unit volume, if there are n number of free electrons per unit volume, then the number crossing the plane in the time dt will be equal to what? N multiplied by the volume. Are you following me, everybody? Are you following, everyone?
Yes, sir.
So you have the n
Yeah.
multiplied by the volume. And if E represent the charge of each electron, then the total charge crossing the area in time dt will be given as what? Multiplied by this electron again. So you have NEAV dt. And so therefore, we can write that our current I is equal to what? The Q dt, which we have established earlier, And the Q is what we have here, and that is placed here. Obviously, you can cross out this change in time, and then you are left with NEVA, where your I stands for the electric current, and N is the number of charged particles per unit volume, and it has a unit of the number of electrons per the volume. That's electrons per meter cube. Then you have your cross-sectional area of the conductor of the wire as A. Then V is the drift velocity, and your E is the electronic charge, which is 1.6 times 10 raised to the power minus 19 coulomb, and it is a constant. Okay? So that is the basic definition of electric currents in a meter. We will still see more of it as we go on. Let's quickly go to Ohm's law. Ohm's law is propagated by a German physicist by the name George Simon Ohm. The man lived between the years 1784 and 1854. And Ohm's law states that the current that passes, take note of those highlighted colors. Is that okay? Ohm's law states that the current that passes through a metallic conductor is directly proportional to the potential difference, provided temperature and other physical conditions are kept constant. The current I is directly proportional to what? To the potential difference. What's the potential difference? The potential difference is the applied voltage to the terminals of the metallic conductor that causes the flow of electron in that material. And so with that, we can write it mathematically that V is directly proportional to I. Is that okay? Where V is the potential applied to the metallic conductor, and I is the current that will flow as a result of the applied potential. Are you following me, everyone? And so the constant of proportionality is the resistance of that material, which is R, and is measured after the German physicist who discovered the law, or who propagated the law. And the unit of the resistance is ohm. Ohm is the unit of resistance, and the symbol is ohm. Ohm is a Greek alphabet, and it has this symbol as you can see on the screen. Okay, so few things are important here. If temperature and other physical conditions are kept constant, then the applied voltage will be proportional to the current that is flowing in that material. Okay, resistance is the property or tendency of a substance that makes them to oppose or limit or restricts the flow of electricity. Now, resistance offered by a conductor is the opposition that material offers to the flow of electricity. I repeat, resistance is the opposition to the flow of electricity in the conductor. I will show you certain illustration to drive home this point, and let's quickly go here. Now, take a look at this. Are you seeing my screen?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now,
Yes, sir.
Yes, sir, we can
Yes, sir.
see this.
if you take a look at this, what can you see here? So, I have a battery here. Are you following me? I have a battery here, I have a conductor here. I have a conductor here. I have wire that is connecting potential from the battery to this conductor. Are you following me, everybody?
Yes,
So
sir.
this ammeter down is measuring the current that will flow through this wire as a result, which is the same current that will also flow through this conductor. Is that okay? Because this is a series circuit. The current that flows through this wire is what will flow through this conductor, which will also flow through this battery invariably. Is that okay? Now take a look at what is happening here.
Yes.
You can see what is happening in this place. These green bubbles are the resistance to the flow of currents by this conductor, by this metal. Is that okay? You can see those electrons are free. They are jumping up and down. And as they are jumping up and down, obviously, they are disturbing or inhibiting the rate at which current is flowing in this material. Now, let's look at what happened. If I go ahead to reduce the voltage, I have 12 volts applied already. Take note of the current that is flowing and take note of what happened here. When the voltage drops, what happened to the flow of current? The flow of current also drops. That explains Ohm's law that says that what? When you apply the potential to the terminals of a conductor, is that okay? The applied voltage is directly proportional to what? To the flow of current in that material. Is that okay? You can see with reduction in the applied voltage, what happened? There is what? With reduction in the applied voltage, there is what? There is consequential reduction in the flow of current. And when there is zero voltage flowing in the material, what did you observe? There is no flow of current because no potential is applied to the material. And because no potential is applied, there is no flow of current. However, what can you notice about some of the atoms, the green atoms in this metal? What can you notice about them? What can you notice about them? They are still moving, even though no potential is there. Some of them are still moving. Is that okay? So that's to tell you the electrons in a metal are not stable. They move. And any little application of potential, let me apply just a small voltage. Then you can see the current begin to flow gradually. Is that okay? I will also show you another one very quickly. I believe you have my screen.
Yes, sir.
Yes, sir.
Okay. So look at what we have. This is another platform to show you what happened. This is a meter and the voltage is connected. Now, increase in voltage gives what? Corresponding increase in current. Is that okay? And decrease in voltage gives what? Corresponding decrease in current. Okay? So, let's quickly go back to the lecture. Now, let's look at resistivity very quickly. Usually the resistance of a wire is affected by several factors. Of importance are the following. Several factors affect the resistance of a wire, the opposition a wire will offer to the flow of current when you apply potential. Several factors affect them, but the important ones are the ones I'm going to talk about. Now, if you have two different wires, obviously, with different lengths, definitely the resistance that will be offered by these two wires will be different. Is that okay? So the length of wire in question will affect the resistance of that wire. And as you can see from this equation down, the resistance of a wire is directly proportional to the length of the wire. So if the wire becomes longer, then you will have more opposition to the flow of current there. And that can easily be substantiated by this. Imagine I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have about 11 free electrons that are opposing the flow of current in this melter. You can imagine if the length of this wire is double, meaning how we have double the number of these free electrons that will oppose the flow of current in that material. And so the length of the wire will directly increase. I repeat, we directly increase the resistance that will be offered by the wire. So if the wire becomes longer, the resistance becomes larger. The cross-sectional area of the wire is another factor that affects the resistance of the wire. The cross-sectional area is another factor that affects the resistance of a wire. Now, what do we mean by this? The cross-sectional area is talking about the size of your wire. If you have a wire with a diameter of say 2 mm and you have another wire of diameter say 8 mm, definitely the resistance that will be offered by these two wires will be different to the flow of current. Is that okay? And I was talking about diameter just now. I believe you know that area of a wire, the cross-sectional area of wire, is given as what? Pi what? Pi r square. Are you with me, everybody? Pi r square. And so,
Yes, sir.
You can say that the area of wire is directly related to what? To the diameter of the wire. This formula can also be written as area of wire will be equal to pi. If you replace your D is equal to what? 2R, isn't it?
R is equal to 2. Yes.
Diameter is equal to what? Hello?
D/2.
So
D/2.
R is equal to D/2, right? So if I place this here,
Yes.
so we have D square
Over 4.
over 4. So you can use either of these to calculate the cross-sectional area of the wire. Are we together? And so by implication, if the radius of the wire or the diameter of the wire is big, then the area will become big. Is that okay? And by implication, since resistance is inversely proportional to area, it means if the area is large, it means the what? The resistance will be small. Let's also look at it from here. The resistance will be small Because if you look at what we have here, if this diameter of this wire, if it becomes bigger, it means there will be more space for this electron to navigate, to escape and flow through. Is that okay? So meaning increase in this
Sorry,
diameter.
sir.
Hello? Meaning increase in this diameter will
Please.
invariably decrease the resistance offered by that wire. Okay? Now, another factor that affects the resistance of a wire is the nature of the material with which the wire is made. For instance, aluminum wire, copper wire, we behave differently. We have different resistance, even if they have the same length and the same cross-sectional area. Is that okay? So the nature of this material we also determine the resistance it will offer to the flow of current. Is that okay? Aluminum wire will behave differently from a copper wire. Is that okay?
Yes,
And another
sir.
factor is the temperature. Is that okay? Another factor is the temperature. Okay? So from this, the constant of proportionality here is R is equal to rho L over A, where rho is the resistivity. Rho is the resistivity of the material. Copper has a different resistivity from aluminium. Copper has a different resistivity
What is
from
wrong?
aluminium. Is that okay? And resistivity of material is measured in ohm meter. Is that okay? So you can see these three factors built into this formula. So if the resistivity is high, then the resistance will be high because there is a direct relationship between them, provided the length and the area is constant. Okay? And we can make rho the subject of the formula, whereby we now have resistance multiplied by the cross-sectional area divided by what? Divided by the length of the wire. Okay? Let's go further
Yes,
and look
sir.
at the effect of temperature. Now, resistivity of a conducting material like metal is increased by even small amount of impurity and varies in temperature. So the temperature coefficient of resistance is defined by this expression, where your R2 is the final resistance and your R1 is the initial resistance. Alpha is the increase in resistance per ohm of the original resistance per rise in temperature. Is the increase in resistance per ohm of the original resistance per rise in temperature. And your delta T is the change in temperature. Maybe temperature move from 0 to 100. Is that okay? Your delta T will be 100 minus 0. Is that okay? Similar variation also apply to resistivity and temperature. The same way, resistance of a material is affected by change in temperature. Also, resistivity is affected by temperature. And the expression for resistivity is also given in this equation you have below here. Okay? Before I go to conductivity, let me also show you quickly a visual illustration of resistivity. Visual illustration of resistivity.
Eagles.
Okay, so you have my screen, visual illustration of resistivity. Now, this is the wire you have here. Are you following me? It has a cross-sectional area here which can be computed using pi r square or pi d square over 4, as the case may be. Okay? Now, let's look at what happened if I increase length. If I increase length, I want you to observe what will happen to resistivity if length is increased. Resistance is changing, right? With increase in length,
Yes.
right?
Yes, sir. Yes, sir.
Now, let us keep length here at mass. Okay, now let's make it flexible. Let's increase resistivity and see what happens to what? To resistance. Increase in resistivity is leading to what? Corresponding increase in what?
Increase.
In resistance. I believe you are following. Are you
Resistance.
seeing this part of the screen?
Yes,
Increase in
sir.
Yes, sir.
resistivity
Yes,
is
sir.
giving correspondence increase in what? In resistance. Decrease in resistivity is giving decrease in resistance. Are you following, everybody? Now let's
Yes,
look
sir.
at
Yes, sir.
area. What happened to resistance when area increases? There is a decrease. And that explains that resistance is inversely related to area. When area increases, resistance decreases. When rho increases, resistance increases. When length increases, resistance increases. Okay? Let's go to conductance and conductivity. We had talked about resistance. Are you following me? We had talked about resistivity. Is that okay? Now, the opposite of resistance is conductance. The opposite of resistance is conductance. Why the opposite of resistivity is conductivity? I repeat, the opposite of resistance is conductance. Is that okay? So, conductance with symbol G is equal to 1 over resistance, as you can see in this place. Conductance G is equal to 1 over resistance. And from this, we can write that what? Resistance is also equal to what? 1 over G. Is that okay by everybody?
Yes, sir.
Good.
Yes, sir.
Then we have, and this unit, it is measured in Siemens.
Yes, sir.
It's measured in Siemens. Conductivity is measured in Siemens. Look at it. Conductivity is measured in Siemens. Is that okay? Conductivity is measured in Siemens with capital letter S as the symbol. Is that okay? Then,
Yes, sir.
let's bring up the formula we had established earlier, that our resistance is equal to what? Rho L over A. Are we together?
Yes, sir.
So, if you bring that to this equation, you will have what is here. Are you following, everyone?
Yes, sir.
Yes, sir.
Good. However, I said earlier that the opposite of conductivity is what? resistivity. So meaning rho is equal to, this is rho, not P, 1 over sigma. Sigma is a Greek alphabet, and that is what is used to represent conductivity. Is that okay? So,
Yes, sir.
since conductivity is the inverse of resistivity, is that okay? So, I write that my rho is equal to what? 1 over sigma. I can also write here that my sigma is equal to what? 1 over rho. Are we together, everyone? Then, if you bring this expression into this equation, I have my 1 over rho here. Is that okay? Then I can bring in sigma. If I use this equation now, if I bring rho into this place, is that okay? Then I will have this expression for my what? For my conductance. Is that okay, everybody? And the unit for conductivity,
Yes, sir.
the unit for conductivity is Siemens per meter. Siemens per meter. Siemens per meter. Sometimes you may see it written as what? Ohm per meter, or per ohm per meter. You might see the unit of conductivity as per ohm per meter. Remember, the unit of resistivity is what? Is ohm meter. So the inverse of it is per ohm per meter. Is that okay? Or the standard unit is what? Siemens per meter. Okay? So I think this what I've explained earlier. Sigma is equal to 1 over rho, and we can write it as what? L over RA. Okay? Let's quickly take from Ohm's law. From Ohm's law, we can write that V over I is equal to R, and we can then bring R, as we have established earlier, as rho L over A. And we can say that our V is equal to what? I rho L over A. Is that okay? The applied voltage can be calculated as what? I rho L over A. You know, you can also go further and express this as what? If we are expressing it in terms of sigma, it will be what? I L divided by what? Sigma A. Do you agree with me? Good. And so, the current density,
Yes, sir.
is given as what? Current divided by area. Current divided by area. The current density in a conductor is given as current over area. And if we bring that into this equation we have up here, then we will have V. We will have V is equal to what? J rho L. And it can also be expressed in terms of what? In terms of what? J L over sigma. Is that okay? Is that okay?
Yes, sir.
Good. So from this, we can say that our current
Yes, sir.
density is equal to what? V over V over rho L, which we can also express further as what? V sigma
P
divided by
sigma
what?
over L.
L. God bless you. Okay?
L.
And so, on and on and on, you can manipulate all these and relate all the formula depending on the particular area of interest. Okay? And then finally, we have this, we have defined this earlier. Then E is defined as what? V over L. This E is talking about what? It's talking about what? Electric field. Is that okay? We saw that in physics 121
Yes.
yesterday. V over D. And then it's given in volt per second. And so V is defined, volt per meter rather. Okay? Electric field that is set up as within the material as a result of the applied voltage is V over the length of the material, which is distance. We made use of that L as distance yesterday. We're talking about the same thing. Okay? So we have V over L here. And then we can say J is equal to what? Sigma E. If you bring it to this previous equation that we have. And we can also go ahead and say that our J, the current density, is equal to what? E, electric field, divided by what? Rho. Okay? Good. Let's quickly talk about superconductivity. There is a class of material that is referred to as superconductors. And superconductors are materials that tend to lose their resistivity or resistance. I repeat, superconductors are materials that tend to lose their resistance at extremely low temperature. And that temperature is called critical temperature. This phenomenon, known as superconductivity, was first discovered in 1911 by a Dutch physicist called H. Kamalinon when he worked on mercury, which is a superconductor below 4.1 Kelvin. 4.1 Kelvin, you know that's an extremely low temperature. Is that okay? Now, one of the interesting area of research for scientists is on how we can get materials that we exhibit superconductivity at a relatively high temperature. And you know the implication of that is if a material can exhibit superconductivity property at a very high temperature, that will be very relevant in solving a lot of problems that relates to energy. Is that okay? Because there will not be opposition to the flow. We say the material has almost zero resistance. Almost zero resistance. No resistance to the flow of current. But the only restriction to the superconductors we have at the moment is this material only exhibit this at very low temperature. And the temperature here is 4.1 Kelvin. That's where it loses resistance to the flow of electricity. Okay? So, let's quickly take a look at a few examples. And then I will give you opportunity to ask questions. Let's look at this example. A conductor. Material has a free electron density of 10 raised to power 24 electrons per meter cube. When a voltage is applied, a constant drift velocity of 1.5 times 10 raised to power minus 12 meter per second is attained by the electrons. Find the magnitude of the current if the cross-sectional area of the material is 1 cm squared. A conductor has a free electron density of 10 raised to power 24 electrons per meter cube when a voltage is applied, and it has a drift velocity of 1.5 times 10 raised to power minus 12 meter per second. Find the magnitude of the current if the cross-sectional area of the material is 1 cm squared. Okay? This is the formula of interest. Recall I is equal to NeVA, where N is talking about the electron density and E is the electronic charge. V is the velocity and A is the cross-sectional area of the material. Okay? Our N is given as 10 raised to power 24 electrons per meter cube. It's already in standard form, so no need for conversion. The velocity is given as 1.5 times 10 raised to the minus 2 meter per second, standard form, no need to convert. And the area is equal to 1 cm square. You can't just use it like this. This is centimeter square. So there's need for you to convert it to what? To meter square. And in doing that, if you want to convert centimeter to meter, you divide by 100 or you multiply by 10 raised to the power minus 2. And in this case, I did multiply by 10 raised to the power minus 2. However, because we are talking of cm square, this square has to be retained here. So I have 1 times 10 raised to the power minus 12 in bracket raised to power 2. Is that okay? If it's a centimeter cube, you will have raised to power 3 in this place. Is that okay? And that will be the meter. So once you do that, is equal to 1 times 10 raised to power minus 4 meter square. There's an omission here. Is that okay? This is meter square. This is meter square. Is that okay? There's an omission in this place, so please take notes. Okay? And so we can apply the formula. So I have 10 raised to power 24, which is my n, 1.6 times 10 raised to power minus 19, which is my e, 1.5 times 10 raised to power minus 2, which is my what? V, and finally 1 times 10 raised to power minus 4, which is my a. So once you punch your calculator, you will get your current and the unit will be in ampere. Is that okay? Is that okay by everybody? Let's quickly look. Let's go to the next example. We have a 12 meter length of a metal wire, has a radius of 0.8 millimeter, and is carrying a current of 12 ampere. If the free electrons of the metal have 10 raised to power 29 free electrons per meter cube, calculate the drift velocity. The same formula is relevant. I is equal to NEVA. But meanwhile, we are interested in calculating the drift velocity, which is I over NEA. Okay? Let's list the supply parameters. L is given in meter and is in standard form, no need to convert. R is radius of the wire that is given and is given in millimeter, so we have to convert it to what? Convert it to meters. So we have 0.8 times 10 raised to power minus 3 meters. Okay? Then the next one is we have current I is equal to 12 ampere standard, and N is equal to 10 raised to power 29 electrons per meter cube standard. Okay? So coming up here, we have to calculate the area. So area of the wire will be equal to what? Pi r square. Okay? So your pi is 22 over 7 multiplied by 0.8 times 10 raised to power minus 3 square. Punch your calculator. You will get the area and the unit will be meter square. Okay? Then your drift velocity can be computed using this formula up here. Is that okay? Is 10 raised to power 29 multiplied by 1.6 times 10 raised to power minus 19, which is your E, and multiply by A, area, which you have calculated here earlier. And once you do that, you get your drift velocity and the unit will be meter per second.